Good morning. Welcome to tutorial 4 on microchip PIC16F877 programming. In this video, you will see the build process, embedded build process in detail. The process of translating the code that is written by human into a code that is understandable by the microprocessor or the controller is called the build process. There are 4 steps involved in the build process. They are preprocessing, compiling, linking, and locating. In preprocessing, the preprocessor strips the comments in the code. It expands the include files, expands macros, and replaces symbolic constants. This is a sample embedded C code. Slash star to star slash. Everything inside this is a comment. And slash slash is a C++ style comment. So the preprocessor strips off these comments from the C code. Expands the include file. If you look here, there are some include files: stdio.h, standardlib.h, xc.h. These files are expanded here. It replaces symbolic constant. Hash defined test file 10. It is a symbolic constant, and this value is used here. Test val 2 greater than test val. Instead of test val, the preprocessor replaces the symbolic constant value 10. It expands the macro. Hash defined square. This is a macro. The value is expanded as 2 into 2 here. These are the steps done in the preprocessing. Once the preprocessing is completed, the next step is compiling. The object code is created from the preprocessed C file. The steps in compilation are parsing and object code generation. The compiler parses the source file to validate the use of variables and checks that the language, grammar, and semantics are not violated. Let us suppose say that in our main.c, we have missed a semicolon. And when we try to build, you get an error, expected a semicolon after expression. The compiler checks the language, semantics, and grammar such that they are not violated. The parsing step also makes a note of the external variables that are used from other modules and variables exported to the other module. The next step is object code generation. The object code is generated from the source file. Some compilers choose to create an intermediate assembly file and invoke the assembler to create object code from the assembly listing produced. Object code generated cannot be executed yet. The compiler works on a single source file at a time. You look here, file1.c, it gets compiled and you get file1.o. File2.c, it is a single translation unit, it gets compiled and you get file2.0. File2.obj. In compiler parlance, each source file is called the translation unit. An object file is created for every translation unit. A translation unit is typically the preprocessed file produced by the preprocessor. The process of compilation ends after creating the object file for every source file. There is no single executable yet. We have different object files. So what does the compiler do? Let us consider two C files, main.c, test1.c in this project. The test1.c declares a variable testvar that is an integer, and main1.c refers to it by an external reference. Since the compiler works only on a single translation unit at a time, while compiling main.c, the compiler can only assume about the existence of testvar and does not know about the exact location of the variable testvar. In case of main.c, the compiler adds the name of testvar to the list of imported symbols when it adds it to the list of exported symbols while compiling test1.c. It is the duty of the linker to resolve these external symbols. This is not limited to variables alone. The linker also links the references to functions that are defined in other source files and libraries. Again, due to the nature of the compiler working with one file at a time, the address of different variables in different files will be assigned a relative value to the particular file. When all objects are linked together to a single executable, the address assigned to all these variables must be unique. The linker takes care of assigning correct address to these variables. Code in a file may also refer to function in some other file. The linker fills these addresses of the functions. Then the code for a particular function may be in a library. The linker will search for the library and link appropriate code with the application. These are the various processes involved with the linker. The output of the linker is a single executable. The linker would have resolved all the external references among the object files, linked up the code from the library, etc. Still, the executable is not ready to run on the target. The final step is called locating. This step finally adds the target specific information into the executable. The programmer must explicitly provide the hardware specific information of location of ROM, RAM, etc. and their sizes. The information can be provided either as a command line option or inside a linker script. A sample linker script is provided. You see here the ROM region, the base address, and the size. Here you have some memory sections RO, RW, ZI. RO is nothing but the read-only section, which is the text section, plus RW is the read-write section, which is the data section, plus ZI is the zero unit section, which corresponds to the BSS segment. In startup script, the memory for ZI section must be allocated and contents must be zeroed. I have made two forward references here. One is the startup script and another one is the memory section. We will see those in the next videos. Thank you.